Ever since I was little, I have loved playing with magnets. Whether it was putting them together, pulling them apart, or even using them to lift other objects like some telekinesis superpower, I really enjoyed playing around with them. Through this interactive simulation of a game, we were able to look deeper into why some of this phenomenon works around magnets. From our childhood, we can see that magnets can apply a force on other magnets. These forces can either be attractive forces or repulsive forces. More formally stated, an electric force is the attractive or repulsive interaction between any two charged objects. Recall from our gravitational equations where we have two objects attracting each other based on their masses. We already have a derived formula for the gravitational force to be Fg equals gm1 m2 over r squared. From this equation, we can see that the gravitational force encompasses the attraction between two objects based on their masses and the distance between the two objects. The electric force is very similar to the gravitational force in regards of the forces between two objects. However, for the electric force, we need to discuss the two objects not in terms of mass, but in terms of charges. Thus, we can compare the two formula, and we can derive a formula for the electric force to be kq1 q2 over r squared. And instead of the masses, we have q1 and q2. These are the magnitudes of the charges of both objects, where both are in coulombs. A coulomb is the amount of current that goes through the object in 1 second. And this current is measured in amperes. So we get an ampere second for a coulomb. So we can also do some unit analysis to find out the K value for Fe. And by isolating for the K in this equation that we derived, we get the unit for K is Newton meter squared per coulomb squared, or kilogram meter cubed per ampere squared per second to the 4. For both Fg and Fe, we were able to also derive these formulas from experiments. So our Fg equation was derived from the satellite lab, which we did some time ago, and Fe was actually derived in the Coulomb law lab that we did along with this project. Let us now compare and contrast these two equations because they're not all the same. So firstly, we can see that for gravitational force, we only have the attraction force because it's only attracting between two masses. Whereas for Fe, we know that objects can either be positively charged or negatively charged, which will lead to either an attraction or repulsion. Also, if you just look at the magnitudes of both the constants of G and K, you can see that the K value is much larger than the G value, which shows that the electric force is a stronger force than the gravitational force. Now that we have an understanding a bit about the electric force formula, let's try putting it into practice with a simple question. So in this question, we have 3 times 10 to the negative 9 coulombs and another object that's negative 5 times 10 to the negative 9 coulombs. So starting with these two stationary objects, we can see that there is a magnitude of electric force between these two objects. And we have a distance of 0.3 meters. So quickly we can use our formula that we already know, F equals kq1 q2 over r squared, and we'd be able to see that, and we'd be able to sub this in, and we get Fe equals 1.5 times 10 to the negative 6 newtons. But there's one problem with this. We know that a force is a vector quantity, and right now we just have a scalar quantity. So as you can see, we don't have the vector arrow on our Fe's yet. And in order to actually add a direction, we need to look at the nature of these charges. So the nature of these charges, you can see that there's a positive charge on the left side and a negative charge on the right side. So as we know, opposites attract. So these two objects actually attract to each other. And these electric forces on both objects that have a different force. So on the left object, we'd have a 1.5 times 10 to the negative 6 Newton to the right, whereas on the right object, we'd have 1.5 times 10 to the negative 6 newtons to the left. And we see that they are both equal in magnitude, but opposite in direction, because that's how an electric force is. It acts on both objects, because just like gravity, it acts on both objects, but they can have the same magnitude, although their magnitude of charges may differ. So that is one special thing to note. Now let's look at this a bit more challenging question in order to see if we really do understand the concept. So in this problem, there are two charges that are placed 1,000 meters apart. Where must the test charge be placed in order for there to be no net force acting on the test charge? So what we can see here is in this question, there are actually three locations in which you can place the test charge. To the left of the first charge, in the middle of the two charges, or to the right of the last charge. So we have three locations. We're going to start off with trying to put the charge in the middle. If we were to put the charge in the middle, we can see that the positive test charge that we have would be repelled by the positive charge on the left and attracted to the negative charge on the right, meaning that both of these vector arrows will actually add up and go to the right, which means that there would be no ability for the two vector forces to cancel out, and therefore the charge cannot actually be placed in the middle. So our next case, we have two options. You can go on the left or the right. Arbitrarily, we go on the left. And what we can see, if we put on the left, actually, we have a repulsion force to the left, and we have an attraction force to the right. And we see that now our vectors are canceling out. However, what we have to do is we have to look at the magnitude of the charges, because the distance now to the left charge is much less than the distance to the right charge. And we can see here that we want the distance to the right charge to be much greater than the distance to the left charge, because the magnitude of the charge of the right one is greater than the left one. So in order to compensate, we know that our formula Fe is an inverse square equation. Therefore, the distance, we want to make the distance smaller to the smaller magnitude charge. Thus, we need to put it on the left. So our location is good this time. And what we should also need to do is, now that we can start solving it, we'll label the measurements and the distances. We'll let the one to the positive charge be x and the one to the negative charge be x plus 1,000. And since we want the magnitude of both forces to cancel out, so the magnitude of both forces to be equal. So now we can go back to our formulas. KQ1 Q test over x squared, KQ2 Q test over x plus 1,000 quantity squared. And what we can see is that the Q test actually doesn't matter. They cancel out in the end. And then the K's would also cancel out. And now you get Q1 over Q2 equals x squared over x plus 1,000 quantity squared. And here you can take the square root to make your life much simpler. And when you solve for x, you actually get x equals 1,000 times the square root of Q1 over Q2, r over 1 minus the square root of Q1 over Q2. And now here you can solve for x, and you got 566.03 meters. Now this is this one case, and in this problem, we should also remember that in the game, because the measurement is depending on the left charge, that it would actually be to the left of the left charge would be a negative value. So we just have to make sure that we understand how the game reads these values. So we'd actually make this as negative 566.03 meters in the game. Now this is one case in which the charge happens to be the left. If both charges are the same nature, then it'd be in the middle. And if the magnitudes were opposite, so like the right charge has a larger magnitude, like the left charge has a larger magnitude, then you actually have the test charge on the right. So there are different cases. You should be able to try out each one and see how the equations you get differ. And our game would actually help you to do these tests. And I hope you guys can try doing the other ones through the game and see how you improve. I hope this helps all of you learning these concepts. And now we will move on to electric fields.
Okay, so now that we kind of understand what electric force is, we're going to move on and talk about electric fields. So given two charged objects, we'll say Q1 as a positive charge and Q2 as negative, we can calculate the magnitude of the electric force between these two by applying Coulomb's law. And then to find the direction of this force, we can just apply a little bit of trigonometry. So then we can see how the net force vectors would react as we move these two around. But let's fix Q1 in place for a moment, and we'll see what happens to the net force vector of Q2 as we move it around. So as we pull a bit further away, the magnitude of the electric force is going to decrease. As we move it closer, it's going to increase. And as we move it around relative to Q1, we can see that the direction also changes. So, but let's take it a step further and imagine what would happen if we place Q2 at every single possible position, filling all of 2D space. Then we get like some diagram like this where it's a whole bunch of vectors pointing radially inwards towards Q1, which makes sense because wherever we move Q2, it's always going to be attracted to Q1, although the magnitude of the attractions can be a bit different every time. Okay, so by looking at all of these net force vectors that Q2 makes, it actually describes what Q1 is doing quite well. It kind of shows what type of effect Q1 is having on the world. And this is actually what we mean by electric fields, which is just like the area of influence that Q1 has. And then the shape of all these net force vectors is what's known as lines of force. So coming out of this actually, this tells us that the lines of force should actually never intersect, because at the point of intersection, that means Q2 would have two different net force vectors, which is impossible. Oh, and from this point onwards, we're going to introduce a bit of terminology. So the central charge that we're going to fix is going to be called the main charge, which is Q1 in this case. And then the charge we move around and see how the net force vector reacts is going to be the test charge, which we are using as Q2. Another important note, the nature or the charge of Q2 should be quite small, so it doesn't interrupt with Q1 and pull it around as well. And another thing you might have noticed is that the nature of Q2 actually matters, because if Q2, let's say Q2 was positive, then instead all of those net force vectors will be pointing radially outwards. So generally we usually have our test charge as positive, but that's just convention. Now that we know that these lines of force are generated by the net force vectors as we move Q2 around, we can actually do the same thing for more than one main charge. So as you can see in the diagram, we're going to have a positive main charge and a negative main charge. So as we move this black test charge around, we can calculate the net force by just adding the effect that the positive main charge has on it and the negative main charge has on it, and taking the resultant vector. And by calculating every single one of these net force vectors, we can actually get a shape that looks something like this. You can see these types of arches as on this side, the positive charge will actually have more effect, so it's going to be pushing it away, and the negative charge is going to have less effect. But as it gets closer, the effect that the negative charge will have increases, so it pulls it closer towards it. And as you see on this line, it's actually completely linear, because the test charge is completely in line with these two, and then there's no other component pulling it up or down. It's only left or right at this point. Another thing we can notice is that all of these force vectors are coming out of the North Pole and going into the South Pole. And this makes sense because the positive main charge is pushing the test charge away, while the negative main charge is pulling the test charge towards it. Okay, so the problem here now is that the magnitudes of the electric field actually depends on Q2, which we don't want. We want an absolute way of describing Q1 without relying on another charge. So if we go back to Coulomb's law, we see that we don't want to have Q2 in our formula. So what we could actually do is just divide out Q2. So we get this formula right here. Epsilon equals electric force over Q2. And by subbing in our value for the electric force, we can cancel out Q2 and just get KQ over R squared. Okay, and this quantity is what we call electric field strength. So by taking a look at the units, which is electric force over Q2, so that's going to be newtons over coulomb. Okay, so now we're in game, and we have this generator, and it wants us to solve this question. So it gives us a main charge, which is negative in this case, and a test charge, which is negative in this case also. And it wants us to pick the correct diagram. So we have this button to switch between the options, and then since these two charges are opposite in nature, we know that they must repel. So the lines of force should be going radially outwards, which we see is this option right here. And if we click next, we get the next problem. Again, this gives us actually two main charges. Both of them are negative again, and then our test charge is negative as well. So we know that it has to be this configuration, not this one. And since the charges are opposite in nature, the lines of force have to be going radially outwards, so it's this option. And if we click submit, we see that we got it right.
Next, we have the electric potential energy question. Before we get started, we must first understand what electric potential energy is. Starting off with just potential energy, it is defined as energy which results from position or configuration. Some examples of potential energy include gravitational potential energy, elastic potential energy, magnetic potential energy, and lastly, what we're going to be talking about today, electric potential energy. The best way of imagining electric potential energy is by bringing two like charges together. The more you try to push them together, the harder it is to keep them together because the electric potential energy is increasing. Now you're one step closer to learning electric potential energy. By using the definition of potential energy and combining it with electrostatics, the electric potential energy of a charge at a point is defined as the amount of work done in bringing that charge from infinity to that point. So, the change in electric potential energy would be delta EE is equal to E final minus E initial. And according to the definition, it would be E point minus E infinity. In addition, by using the work energy theorem, which states that work causes a change in energy and work shifts energy from one system to another, we can set it equal to negative work. What we realize from E infinity is that it's very similar to the gravitational potential energy to distance graph. And the electric potential energy to distance graph, as the distance increases, in both cases of attraction and repulsion, the potential energy is seen to decrease. Thus, we can say that as the distance approaches infinity, the electric potential energy will be zero, making the equation become E point is equal to negative work. Now, how do we solve for work? Normally, if the force was constant, we would use mechanical work, which is F dotted with displacement. However, we cannot do that with electrostatics, as when taking a look at the equation Fe is equal to electric field times charge, we know that the electric field's strength changes depending on the distance, meaning the force is not constant. For example, in the electric potential energy to distance graph, in order to find work done, we would need to take the area under the graph, which is also known as taking the integral. Since taking the integral would take a lot of work, what we can do instead is look back in the unit of gravitation, where we did something similar by taking the area under the graph using the geometric mean to get an approximate answer. Instead of doing all that complicated work, we'll take the formula we got in gravitation and use its similarities to our advantage. This is the gravitational potential energy formula compared to the electric potential energy formula. As covered in Anish's lesson, the G value is replaced with the K value while the masses are replaced with charges, since we're now looking at electric potential energy. From our past experiences in this grade 12 year, we know that the SI units of work and energy is joules. So to make sure that this formula is correct, let's check if the K units found in Anish's lesson on electric force will result in joules. So the formula we have for electric potential energy is KQ1Q2 over R, and the K units that Anish found were Newton meter squared over Coulomb squared. By subbing in the K value, we get the units as Newton meter squared over Coulomb squared times Coulomb over meter. Since the two coulombs will result in Coulomb squared, the Coulomb squareds cancel out, while meter squared over meter will also cancel out, resulting in Newton meters, which is essentially joules. This verifies that with unit analysis, the electric potential energy formula does indeed work. So the first problem states that given the distances between adjacent charges is 70.00 meters, calculate the total electric potential energy of the group of charges. So this problem is relatively easy, as you just take the electric potential energy between every two charges. In this case, the total potential energy will equal K times 2.05 millicoulombs times negative 8.89 millicoulombs plus 2.05 millicoulombs times 7.56 millicoulombs plus negative 8.89 millicoulombs times 7.56 millicoulombs, all over 70 meters. Then once you just plug this into your calculator, you get your total potential electric energy to be negative 8,991.63 joules. The question states that given the distances between adjacent charges is 64 meters, calculate the total electric potential energy of the group of charges. This problem is a lot harder since there are 4 charges and you cannot simply take the potential energy of 2 adjacent ones and call it a day. So in order to get total potential energy, you need to take the energy among every 2 charges. So in this case, I split it up into adjacent and cross to make it easier for the workflow. So for adjacent, you just take every 2 charges that are connected to each other, like normal, and then for the across, there's only 2 possible cases here, where you take the 5.81 and the 8.71 as a group, and negative 6.82 and negative 1.84 as a group. Once you get those 2 potential energies, you can add those 2 to get the total electric potential energy to be negative 11,402.81 joules. With this, you'll be able to solve all types of questions involving total potential electric energy.
Now, while we are already familiar with electric fields, we must expand upon something that uses the concepts and formulas related to electric fields extensively. We must discuss parallel plate capacitors. Simply put, a parallel plate capacitor is just 2 identical parallel conducting plates that are large in comparison to their distance separation. Arranging these plates in this manner will create attraction between the charges on the plates, drawing more charges to the inner surface of the plate. There is a potential difference between the 2 plates, and so work will only be done on a particle between the plates when it travels non-perpendicularly to the electric field. If a particle were to travel perpendicular to the electric field, the potential difference would be zero, as the particle would go down an equipotential line. That is, a path where the potential doesn't change. If we put a positive test charge between the two plates, the test charge will be repelled by the positive plate and will be attracted to the negative plate. If the positive plate is directly above the test charge and the negative plate is directly below the test charge, the net force exhibited on the test charge will be straight down. Since the field lines from the positive plate to the negative plate are parallel to each other, we can say that the electric field is uniform throughout, except at the edges of the plates. This is known as the edge effect. To summarize, the electric field produced is constant and perpendicular to the plates. Some more key concepts to note are that the magnitude of the electric field's intensity at any point is directly proportional to the charge on each plate. This can be rewritten as epsilon is proportional to Q, where Q is the charge per unit area on each plate. Now that we understand how parallel plate capacitors work, we must apply our knowledge to a type question that is based on a famous practical experiment, Millikan's oil drop experiment. This type of question, which we have dubbed as the oil drop question, goes as follows. For an oil droplet suspended between two parallel plates, identify the correct number of excess or deficit electrons given the mass of the oil drop, distance between the plates, location of the positive and negative plate, and potential difference between the plates. Now, before we solve this question, it is pertinent to note that the oil drop being suspended between the plates means that the oil drop is in static equilibrium. There are only vertical forces acting on the oil drop. We know that the force of gravity will accelerate the oil drop downwards, but since the oil drop is in equilibrium, the electrostatic force is responsible for keeping the oil drop from moving. If the summation of forces equals 0, and the net force, 0, is the sum of all the forces, that is the electrostatic force and the force of gravity, then we can say that the electrostatic force plus the force of gravity equals 0. We know that Fe, or the electrostatic force, is equal to E times Q, and that Fg is equal to mass times gravity, or m times g. So we can rearrange Fe plus Fg equals 0 to equal Eq equals mg. E can be rewritten as potential difference over distance between parallel plates, meaning that delta V over R times Q equals mg. If we rearrange this to solve for the charge, we get Q is equal to mgr all over delta V. Plugging in our givens, we can determine what the charge is. If we rearrange the formula Q equals Ne in terms of N, the number of electrons, and sum in the charge we found into Q and the charge of an electron, which is 1.602 times 10 to the negative 19 coulombs, into E, we will know how many excess or deficit electrons the oil drop has. Finally, since the negative plate is on the bottom and the positive plate is on the top, we will know that the oil drop must possess an excess of electrons. To fight against the pull of gravity, the oil drop must be negatively charged and experience repulsion against the negative plate that is below the oil drop. Okay, let's solve a sample oil drop question from our game. Let's examine our givens. We know that the mass of the droplet is 3.2 times 10 to the negative 15 kilograms. The distance between the plates is approximately 3.965 times 10 centimeters apart, and that the potential difference between the plates is 777 volts. Additionally, we can put the distance in terms of meters and say that the plates are 3.965 times 10 to the negative 2 meters apart. We are asked to determine the number of excess or deficit electrons the oil droplet has. We know that the formula to determine the number of electrons is Q equals Ne, where Q is the charge and E is the charge on an electron. The charge on an electron, E, is already known to be 1.602 times 10 to the negative 19, so we must solve for the charge Q to determine N, the number of electrons. Let's examine the forces acting on the oil drop in order to solve this question. Gravity is pulling the oil drop down, and the only other force acting on the oil drop is the electrostatic force. Therefore, the electrostatic force must be pulling the oil drop up and must be equal to the force of gravity in order to keep the oil drop suspended. Since Fnet equals 0, and Fnet is the sum of the electrostatic force and the force of gravity, we can say that Fe, which is the electrostatic force, plus Fg, which is the force of gravity, equals 0. We know Fg is equal to mg, and that Fe is equal to Qe, so we can rearrange the equation to say that Qe equals mg. We can recall that E equals potential difference over distance between the plates, and so Qe equals mg becomes Q times delta V over R equals mg. If we rearrange for Q and sub in our givens, we get Q equals 3.2 times 10 to the negative 15 kilograms times 9.81 meters per second squared times 3.965 times 10 to the negative 2 meters all over 777 volts, which equals approximately 1.602 times 10 to the negative 18 coulombs. Subbing this into our first equation of Q equals Ne and rearranging for N, we can see that the number of electrons equals 1.602 times 10 to the negative 18 coulombs over 1.602 times 10 to the negative 19 coulombs, which evaluates to approximately 10 electrons. Now, we know that this is in excess of 10 electrons as the negative plate is on the bottom. To pull against gravity, the oil drop must be repelled by the negative plate and attracted to the positive plate, so it is pulled upwards to counteract gravity. This requires the oil droplet to have a net negative charge, which would mean that the 10 electrons present are in an excess. Okay, let's solve a sample oil drop question from our game. Let's examine our givens. We know that the mass of the droplet is 3.2 times 10 to the negative 15 kilograms. The distance between the plates is approximately 3.965 times 10 centimeters apart, and that the potential difference between the plates is 777 volts. Additionally, we can put the distance in terms of meters and say that the plates are 3.965 times 10 to the negative 2 meters apart. We are asked to determine the number of excess or deficit electrons the oil droplet has. We know that the formula to determine the number of electrons is Q equals Ne, where Q is the charge and E is the charge on an electron. The charge on an electron, E, is already known to be 1.602 times 10 to the negative 19, so we must solve for the charge Q to determine N, the number of electrons. Let's examine the forces acting on the oil drop in order to solve this question. Gravity is pulling the oil drop down, and the only other force acting on the oil drop is the electrostatic force. Therefore, the electrostatic force must be pulling the oil drop up and must be equal to the force of gravity in order to keep the oil drop suspended. Since F net equals 0, and F net is the sum of the electrostatic force and the force of gravity, we can say that Fe, which is the electrostatic force, plus Fg, which is the force of gravity, equals 0. We know Fg is equal to mg, and that Fe is equal to Qe, so we can rearrange the equation to say that Qe equals mg. We can recall that E equals potential difference over distance between the plates, and so Qe equals mg becomes Q times delta V over R equals mg. If we rearrange for Q and sub in our givens, we get Q equals 3.2 times 10 to the negative 15 kilograms times 9.81 meters per second squared times 3.965 times 10 to the negative 2 meters all over 777 volts, which equals approximately 1.602 times 10 to the negative 18 coulombs. Subbing this into our first equation of Q equals Ne and rearranging for N, we can see that the number of electrons equals 1.602 times 10 to the negative 18 coulombs over 1.602 times 10 to the negative 19 coulombs, which evaluates to approximately 10 electrons. Now, we know that this is in excess of 10 electrons as the negative plate is on the bottom. To pull against gravity, the oil drop must be repelled by the negative plate and attracted to the positive plate, so it is pulled upwards to counteract gravity. This requires the oil droplet to have a net negative charge, which would mean that the 10 electrons present are in an excess.